Hello again. Let's get into section 9.3 today. Right? As I mentioned last week, I kind of pushed 9.3 to its own day because it's kind of an interesting, unique subject matter. So better to spend the extra time with it exclusively. All right? Anyhow, this is called Modular Arithmetic, right? And it's based upon what we have already developed, which is mathematical systems. So a quick review of that, right? What involves a mathematical system? Two conditions. Number one, if you have a mathematical system, you must have a set, right? Which means that you would see something potentially in fancy braces, right? The example that I had used a while ago was clock 12 arithmetic. So in clock 12 arithmetic, the set would be everything from 1 to 12, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay? And the second condition is that you would have to have some binary operation, which means that it's either usually adding or multiplying. And in the case of clock 12 arithmetic, it is frequently just adding. So you would say the system is clock 12 arithmetic, a set of 1 to 12 under the binary operation of addition. Something like that. Now, what we're going to do is basically take this and tweak it ever so slightly to change it into a modular form of arithmetic. All right? And in that event, all that really is going to happen is that we are going to modify the set. The set would become, if I'm sticking with clock 12 arithmetic, almost all of the same elements except that we're going to be starting from 0. And therefore we would have to stop at 11 in order to keep it as being 12 unique elements. So you would see something like this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and that's the end of it. Right? We're excluding 12 because we're compensating by starting with 0. Okay. All right. And whenever you see something like this, all right, that is now this alternative form of the first of two things. These would be referred to collectively as a modulo 12 system in this example. Use this word modulo. All right, it would still have whatever the operation is under consideration. Right? The number of contents, basically, the number of elements, in this case, again, using clock 12 arithmetic as an example, this is referred to as the modulus. All right, so know that phrase, and just know that we're going to be referring to these as modulo, whatever the number is of elements. Right? And even still, further still, they sometimes abbreviate that as simply mod, and then the number. So mod 12 in this case. All right. Basically, modular arithmetic systems, under addition especially, are useful when you have a cyclical or repetitive sort of arithmetic. You know. So I'll give you a couple of examples. All right, let's see. What could you do with this? Well, you can predict the day of a week that is identified by the name Monday, Tuesday, what have you, several days from now, or, potentially, hundreds of days from now. So let me give you an example of that. I may have to get a paper towel, but let me erase this and see how well it's working out. Looks like it's okay. My green usually is stubborn, so a little bit of the red too, but it's working nice. Very cooperative today. Okay. Let's see. All right, oh, that's great. All right, let me start with this. We'll have an example. Where can you use this? All right, we're going to use this to predict. This is not the best of those. Let's see. Day of the week. All right, several days from now, or from some starting point. Okay. All right. Imagine you had these conditions. All right. If today is Sunday, it is not, it is technically Monday today. But let's say that it was, all right? What day will it be in 23 days? In that event, what we could do, to sort of ease into the subject of modular arithmetic, is think of time. Take a clock, for example, which is cyclical, right? And adapt it. Instead of a clock usually being something like, would have 12 increments on it, as we read in increments of 12, unless we're doing Navy time, right? And then instead simplify a clock so that it doesn't say hours, but instead reads days. So I made a little stencil, and I'll start with that. All right. See if this works out. We had pizza recently. And I'll use this just to trace for a moment. Humor me while I do this. I just want to make as nice a circle as I possibly can. Okay. Close enough, right? What I actually took the time to do is also increment this. So I'm just going to make little marks here, and here, and there, and there. Okay. And label it. Let's just say at what would normally be the point of 12, all right? We'll make that the start, we'll call it Sunday. And then the next increment will be Monday. And then Tuesday. And then Wednesday. Should be Thursday. And Friday. And finally Saturday. Okay. If you make a clock that is labeled as such with days, and there would only be 7 naturally, because of the way that we have the calendar arbitrarily chopped up, right, a week, then you could basically count through cycles until you count 23 individual days and see where you land, right? Making sure that you start on a particular day. Now, where we're going to start in this case is Sunday. So I'm going to start here and end wherever, all right? 23 days clockwise. Right. Which means we're going to read like that, of course. All right. What I also did was I made a little dial here. It's very lonely this weekend. I took the circle that I cut out and I made a little dial, see? Kind of cool, right? anyhow, what I'll do is I'll have this sort of situated here, and everything lines up where it's supposed to be. And I'll count through cycles, right? Now I can go very slowly, starting at this, and then maybe start to observe a pattern, all right? So let's see where we land, all right? If this is 0, this is 1, 2, 3, 4, 5, 6, 7 days, 1 week, and we're already right back where we started. That's natural, right? That means that in theory, you could do this in steps of 7, all right? To complete one whole cycle takes 7 steps. So what's another 7 after 7? 14, right? So I'm gonna land here on the 14th count. So this would be 8, 9, 10, 11, 12, 13, 14, all right? And then, okay, we're getting closer to 23, but still shy of it, all right? So go another 7, which would be what? 21, all right? Would be right here. 15, 16, 17, 18, 19, 20, 21, all right? Until finally, we've hit 21. We're not going to complete another cycle of 3, there would be just 3 as the maximum complete cycles. And then I'm going to go the extra amount, all right? So if this is 21, this is 22, and that's 23. So that is basically where we would stop on Tuesday, all right? All right? And that would answer the question, all right? What day will it be 23 days forward from Sunday? It would be Tuesday. Right. Now, as you can see, it's kind of cumbersome, all right? I have to start breaking out a piece of cardboard, and making a device basically for calculating this. But, all right, this is where modular arithmetic is coming from. The idea of something being cyclical, all right? So there's a repeated pattern, all right? And we could use arithmetic to basically do what we would do with a device. So it's more in your mind than it is in life, right? More in theory than in practice, you might say. All right. Now, if I were going to take the system that has been created here and adapt it to modular arithmetic, here's what you would read. Well, here's how you might go about that process. Start with a model. This will be our model that we would fill in for any problem. Right? We would call this a modulo M system. All right. And the M is the so-called, I should say so-called, it is what it is, modulus, which is basically the total number of increments. All right. So in the case of a calendar, it's 7 days. All right. So we're going to call this a modulo 7 specifically system. Okay. And if we want to get fancy, all right, we could just shorten this to, okay, it's a mod 7 system. A lot of times it's written in shorthand like that. Green is a bit faint. See if I can write this a little bit better. That's nice. Okay. Mod 7. I do often put it in parentheses. Right? In a mod 7 system, right, specifically this one, if we're going to be less verbal and more numerical, right, more symbolic, right, then if it's a system, of course, it has to include those 2 points. So it has to be a set. So let's define the set. The set would be, if it's modulo, starting with 0. So 0, 1, 2, 3, 4, 5, 6. And it would, perhaps somewhat counterintuitively, end at 6 because we're compensating with having a 0 here. Right? 0 is the start as opposed to 1. Right? And since we would want, in theory, not just to qualify as a system, but to make this practical, the kind of arithmetic that would be involved in this case would be addition. The binary operation would be addition. Got a different column. Okay. What we are accomplishing at this point is just taking something and trying to make it more mathematic, right? More symbolic than it had been, right? Notice that I'm using numbers to represent the days of the week rather than writing Monday, Tuesday, Wednesday. Nothing wrong with that, but this is a slimmed down version of that set. Right? This is the set, this is the operation. Okay. When working in a modular system, a table is often handy. So what I did is I stole some tables from the textbook that you guys have, and I'll have it available in Canvas. Basically, the printout that you would have gotten today looks like this. Right? It's really these two. Right? Table 911 and table 912. Right? This is how you could calculate what number represents a day. Right? If this is Sunday, Tuesday, Wednesday, Sunday, Monday, Tuesday, Wednesday, 3 would be Wednesday, say, for example, right? You could use this table by reading the first addend, that is the first number in your binary operation, and then crossing it with how many days forward you want to count, all right? So these are basically the numbers where you would start from, all right? And these are the numbers that you would add to it, all right? It's good to have this table for the same reason it's good to have a table for clock 12 arithmetic, because it is a funky sort of addition. You could figure it out if you truly had to, but to have a table is to have a tool, all right, that'll make the operation a little easier to get through, all right? It's not intuitive, right? Anyhow, have that on hand as we discuss, all right? Let's see. Let me erase this, and then I'll give you another example of some more information. Okay. This is our established Mod 7 system, all right? It really would work for anything that happens to be, 7 steps. But let's say we were going to do a calculation with this. All right. Bear in mind, I keep picking the wrong one. Right. If you were going to calculate, there is, of course, regular ordinary arithmetic. And then there is this bizarre sort of Mod 7 arithmetic. Just to see the benefit of having a table, right? You know very well, right, that if you added 4 plus 6, right, that you would get 10. All right? That is what ordinary arithmetic has trained us to decide, all right? All right, we use this symbol to represent that amount, all right? But if you're in a modular 7 system, all right, the maximum is actually 6, all right? So when you're considering the arithmetic, in this case it's addition, using a maximum of 6 and then cyclically working back to the beginning and counting forward, all right, another 4, all right, you're going to land in a different place that is not the number 10. All right, again, the reason why you would want a table, because the table has already figured this out, all right, rather than sit there and scratch your head. You can figure it out, all right, but learn to use the table is the point of this. If you did the same thing, (4 plus 6) in a mod 7 system, all right? Let's use the table and we'll calculate, all right? I'll show you the nice table here, all right? Here's our table, all right? If you're gonna say start with 4, as if this was the 4th day of your system. Never mind that 4 is a Thursday, it doesn't matter, right? For right now. You're starting with the number 4. What you're going to then do is then cross-reference this with 6 days forward from there, all right? Where does that land you? It lands you on the 3rd day, because once you hit 6, that's the maximum. It has to restart, right? In theory, if you went to a maximum of 6, right, and then counted another 4, 1, 2, 3, 4, you would be on the 3. That's where it's crossed here. Notice that they circled in the table, all right? That the arithmetic for mod 7 works out to be 4 plus 6 is in fact 3. This is the equivalent of basically saying Thursday. Ooh, that's the end of that red. What a shame. Okay, I have more. Right, it's the equivalent of saying, oh, Thursday, right, plus 6 days. All right, so Thursday is your start, all right? The end of the week, all right, is, I suppose it's Saturday, right? Friday, all right, is 5, all right? Saturday would be 7, all right? Sunday, Monday, no, it's not working out quite right. Friday. So I'm just curious if this is something you could do by hand in theory. Friday, Saturday, Sunday, Monday, Tuesday, all right, Wednesday. It does work, all right. It is something that you could figure out if you absolutely had to, but again, better to have a table established, all right, or at least utilize one that has been, right. Friday, Saturday, Sunday, Monday, Tuesday, Wednesday. Wednesday, there you go. Thursday plus 6 days equals Wednesday. That makes sense, right? Because if it was exactly 7, it would be Thursday again. Okay. All right. Anyhow, to have a key is handy. All right. Let me erase this and sort of draw you a diagram of options that you have. The red is pesky too. All right. I do like writing in red, but unfortunately it gives you trouble. When it comes time to erase, anyhow. Right. Anyhow, calculating a problem like this, you have 3 sort of methods that we've discussed at this point. We have a physical, the clock that we had adapted, which I would not advise anybody to have to do, but it is the first thing that we considered, all right? A second thing is to employ a table, right, that has been established. Which is great if it has been established, all right? And then there's this sort of formula, if you will. Which is kind of the go-to method, really. Okay. And the formula is this. I'm going to write it up here just for the sake of space. Well, maybe I'll write it here since it's underneath this heading. You take the operation of binary terms and then you divide by n. I'm being kind of vague in this sense. The operation is usually addition, so it'll be the two things that you added first, all right? And then divide by m, and m again is the modulus, which is the number of increments, the number of contents, the elements of the set, all right? And then after you've done that, all right, I'm not going to write nicely. Okay. Read whatever the remainder is. The remainder is basically the translation of the regular sum into the modulus 7 sum in this particular example, right? You write that for reference. The remainder is the translation. The translation of regular ordinary arithmetic into the specific mod arithmetic. All right, we'll do an example. And I'll put it here. All right, so if I'm using this formula, it's going to be a sum in this case divided by the modulus number, all right? And then as an afterthought, we're going to look at the remainder. Okay. The sum of 4 plus 6 is still 10 under the conditions of regular ordinary arithmetic. And I'm still going to do basically regular ordinary division, right? But I'm going to, rather than pay attention to the main portion of the quotient, I'm going to zero in on what just the remainder is. What would be the modulus in the case of the examples we've been talking about? 7. So I'm basically going to divide 10 by 7, right? And in that event, I would encourage you to sort of, if you're doing this by hand, and you most likely would be, all right, draw the sort of old-fashioned division box, all right? In the United States, at least, that tends to be written like this, oriented like so, all right? And you put the numbers on the inside here, 10 being on the left of the symbol goes inside the box, and 7 being on the right side of the symbol goes outside the box. Dividend and divisor respectively. Right? Then mark out the intricate details. Right? How many 7s can you squeeze into a 10 roughly? Right? 1 whole 7. Do the actual subtraction. Right? 10 minus 7 is just 3. And you're not, bear in mind, you're not doing decimal division, and you're really not making fractions either. The sort of type of division that you're doing is more in keeping with the most fundamental form of it that you may remember if you maybe in first or second grade when they first introduced the concept, right? What they would have done when you ran out of digits here is they would say, oh, well, for right now, just put R and then the number 3, right? Whatever the difference would have been here, since you've run out of numbers, you're not going to put a 0 and carry it down to 30 and continue with a decimal. You're just going to call it remainder 3. All right. Anyhow, this is what we're after, because that is the translation of from regular arithmetic into modular arithmetic. Basically, the point of this is to say that 10 is really 3 in this system, in a mod 7 system. Right? There's in fact a symbol that we would use that's less verbal, but this is what it means. All right? All right. So anyhow, yes, you could use a clock if you wanted to again. All right. If you're inclined to design a clock that has 7 pi wedges and these lines are days of the week, and then count. If this is in fact Sunday, all right, or if you wanted to start on Thursday, it'll drive you crazy, but you would have to do something like this. And then move. Right. In the case of the problem that I just discussed, that we're starting with the number 4, right? This is really 0, 1, 2, 3, 4. You would be starting here. So your dial, right, would be aimed at 0, 1, 2, 3, 4, Thursday, all right? And then you would add 6 to that, all right? 1, 2, 3, 4, 5, 6, all right? And then you would be on Wednesday, naturally, okay? I like that. I mean, I took the time to make it, but it's an obstacle because you'd have to draw and construct a thing like that. Anyhow, alternatively, again, you could refer to a table, all right? Start and then cross-reference how many days forward. You go to a maximum of 6. All right, and that equates to the day number 3. Day number 3 is Wednesday, all right? If Sunday is 0, all right, then Wednesday is the 3rd day. Let's see. Numeral 3, okay? Let me get back to this. Rather than refer to something in this cryptic verbal way, let's get into the symbol that you have as an alternative. These things you would say are congruent, and there is a congruency symbol. 10 is congruent to 3. Okay, let me erase this. Discuss congruency. We would say A is congruent to a second number B, and that is illustrated like this. A written first, sort of an equal sign with an extra line. Right? If you've taken geometry, you probably are familiar with the congruency symbol there, which is to say the two angles are basically equal. They would be an equal sign and then a sort of the similar curve like this above it. Right? In this case of modular arithmetic, they resort to using 3-line equals, if you will. Okay. A is congruent to B is abbreviated or written as, or written like this, for the sake of abbreviation. And then they would specify the system. So the problem that I keep beating here is mod 7, right? Or mod M, right? to generalize. You should specify that, all right, because the congruent numbers would be different based upon what the modular system is. You know, if it had more increments, you'd get a different value than, say, if you had less increments. All right. And one thing that is true is that you can figure out what something is, or prove that they are congruent. That is to say, A is congruent to B if A and B have the same remainder. Do remember that, it will help you a lot. It is proof that these things are in fact congruent. Let's do a couple of examples now. Let's see. Okay, I'll do this right underneath it. It's on its way out. And a marker. All right. Let's say that you were asked to show that 10 is congruent to 3. All right, in mod 7. All right. All that means is that you basically have to divide each of them by 7. So you would take 10 and divide by 7. And you would take, even if it sounds strange, 3 and divide by 7. Okay, now in this case, how many 7s again could you fit into it? Just 1. And the difference, of course, is 3, which means that the remainder is 3. We had done that already, right? If you tested out 3 itself, right? How many 7s can you fit into 3? 0, right? But you'd still go through the motions, right? The quotient times the divisor is the number that you subtract here. So 7 times 0 is just 0. The difference would be 0, and you'd say, yes, it's remainder 3. It's kind of peculiar to do that at this stage in our mathematical life, right? But that is really how it would work out, right? The remainders would be the same. So you could say with certitude, these are in fact congruent. 10 is congruent to 3, right? In a mod 7 system. Okay. Let's do another. Are we on time? Good. Let's change the system because it's been kind of redundant. Consider this. Consider 37's congruence to the number 5 in mod 8. A couple of things that you could sort of glean from just that much information given to you, right? And I would sort of get in the habit of writing it. If you're working with a mod 8 system, right, that means that you have a set, all right, and in theory the set would look like this. Starting with 0 always for modulo systems. 0, 1, 2, 3, 4, 5, 6, and it would go up to 7 because the last term is always whatever the modulus is minus 1. Right? And this is the modulus m here. So it would be 8 minus 1, that logically would be 7. Right? The second condition is that it would have to involve a binary operation. If they don't specify, then don't invent one either. Let's see. If I were to divide 37 by 8, we'll figure out what the remainder would be. And then simultaneously, we'll figure out what 5 divided by 7 would be. Pardon me, 8. Because we're doing 8s. Fixated on 7. That's not good. Okay, so how would it work out? How many 8s can you squeeze into 37? Good to know your multiplication tables. 8 times 4 is 32. That's the maximum, really, of complete cycles. Right? The difference of these would be 5. So your remainder would be R5. Right? If you did this arithmetic, you'd have a similar situation as to before, which is that you can't fit an 8 in 5. So you would say, well, 0 8s fit into 5. But still subtract, right? The quotient times the divisor is the number that goes here, right? And the difference would still be 5. And you would say it is 0 remainder 5. How peculiar that is, right? Right. If this and that have the same remainder, right, then it is safe to say 37 is congruent to 5 in a mod 8 system. Is. And that's the congruency symbol. Okay. Now, here's the next sort of logical step in this conversation. All right. Let me write this in red. Numbers with the same remainder which is to say congruent numbers can be categorized to a modulo class basically if you have several numbers, and there in theory would be an infinite number of them that end up with the same remainder, you can categorize them as going, okay, these things will belong to the same category, right? The same modulo class. Right? And to that effect, there is yet another table. In theory, every number, in the universe of infinity, infinite numbers is congruent to one of the numbers in a modular system. Right? And that table that I mentioned before, 912, it actually illustrates that for 7 again. Right? Let me point to this now for reference. Right? In this table, 912, all of the things that are in the same column would end up having the same remainder. So therefore they would all be congruent, and these would all be unique modulo classes, right, for mod 7s in particular. 0 is congruent to 7, congruent to 14, 21, 28. 1 is congruent to 8, to 15, to 22, to 29, looks like backwards, yes. All right, and so forth. 3 is congruent to 10, 17, 24, and 31, all right? The reason for the ellipses is this would go into infinity. You can't possibly, figure them all out. It would take the rest of your life, and even then you never finish. It would be futile effort. But, all right, again, to have a table would help. And some of the questions you get in my lab are asking you to go, well, what would it be, several steps down the pike? Right? we'll do a couple of examples. All right. Let's see. Let's try this. And I'll use the table to verify, just to kind of get your feet wet. Suppose, using division, we set about the task of determining which numbers in a MAT-7 system are equivalent. And I'll say congruent. Okay. And we'll do 3 of these. We'll do an A, we'll do a B, and we'll do a C. Okay. What is 60 congruent to? What is 84 congruent to? What is 412 congruent to? And notice that these are actually outside the scope of the table, so we really couldn't use it now that I think about it. But we could still figure it out, right, using division, right, and staring at, specifically the remainder. All right. What is really happening here is that we are taking each of these things and essentially translating a regular ordinary number into a specific mod version of itself. An element from a specific mod. Okay. So if we're sticking with mod 7, because I really shouldn't bother, but hey, that's just taking 60 and divided by 7. All right, and we'll do 84 and divide by 7, and we'll take 412 and divide by 7. We'll see what we get. How many 7s can you squeeze into 60? Again, to know your multiplication tables is handy in this event. Let's see, 7 times 8 is 56. That's just shy of it. And the difference of 60 and 56 would be 4. So that means that the remainder would be 4, and therefore 60 would be congruent to the number 4. All right. You translated a regular number, all right, into a mod 7 number. In this particular case, a mod 7 element would be better to say, I suppose. All right, we'll do the same thing here. 7 can squeeze into 8 once. Do the arithmetic 1, drag down 4. 7 goes into 14 exactly twice, which is 14, and the difference is 0. And you might go, oh, well, there isn't a remainder. Well, technically, this is the remainder. Remainder 0. So what you would say in an event like this is that 84 is congruent to 0. We've translated a regular number into a mod 7 element. All right. One more of these. All right. How many 7s can you fit in 4? Not enough. Not right. I'd read it as 41. 7 goes into 41 roughly. 6 would be 42, so 5. 35. The difference would be 6. Drag down 2. 7 goes into 62 again about 8 times, which would be 56, and the difference would be 6. So your remainder would be 6. And you would say, therefore, that 412, well beyond the scope of the table, right? It could be said with certitude is equivalent or congruent to 6. Okay? Right. Then, of course, if we were talking about calendar days again, you could translate this number into day of the week that refers to 6, which would be Saturday, I want to say, right? So 412 days forward from Sunday, right, would be a Saturday, is how you would translate that. Let's see. Okay. Okay. Let's continue to evaluate here. On time, good. Let's evaluate each example in Mod 9, a Modular 9 system. Right? Again, even if it seems like overkill, I would just be clear on what Mod 9 really means. Right? It means that you would have set elements of 0 to 8. Right, because the last one is m, the modulus is what 9 is, right, minus 1. Okay, that means that whatever numbers are given to you, you're going to translate them into one of these elements. So here again we'll do an A, we'll do a B, and we'll do a C. In this case, suppose instead of just a standalone Arabic numeral, you had an operation, a binary operation handed to you. All right, you could still get through it. So we'll have 7 plus 8, and 8 minus 5, and then a product, 7 times 5. What we would do is perform the ordinary arithmetic, right, to establish the number. Right, then translate the outcome. The outcome could be a sum. The outcome in this case could be a difference. Or the outcome could be a product. And how do we do that? By dividing. Right? Divide. Oh man, my green is fading out on me. Green is always so much trouble. More trouble than you're worth. What about this one? Yep, that's getting all right. That's all right. Not my favorite. Okay. You would stick a number here and a number here, and then consider what does the remainder equal. Okay. Okay. So in this case, right, if you stuck with the ordinary arithmetic, you know that 7 plus 8 is actually 15, right? Then, just kind of squeezing this in here. If you took 15, right, and took that sum, or whatever the operation is, and divided by the modulus. All right. That's a little bit hard to see with the reflection. I don't know if that's any better, but we'll see what we get. Operation in this case happens to be this number here, and then divide by the modulus. So, let's see, the modulus for mod 9 is dividing by 9 then. I'm running out of space, so I'm going to try to squeak this in, limit myself to that much space here. 15 divided by 9. How many 9s can you squeeze into 15? Roughly 1, which is 9. And the difference would be 6. That's the remainder. So therefore, 15, I'll make this more prominent. 15 is congruent to 6, right? And therefore a person could say that 7 plus 8 is congruent to 6, right? In both of these cases, specifying that it is mod 9 system. Defied my own squiggle here. There we go. That's terrible, but you get the point, right? You figured out what the number would actually be from adding, all right, and then figure out what the remainder is to say, okay, this is congruent to that. Okay. All right, in this case, same thing, all right? We're going to start out with the ordinary arithmetic, all right? And we know very well that if you subtracted 8 and 5, you'd get 3. All right. So let's now divide, even if it seems silly, 3 by modular 9, modulus 9. Let's see. You're going to get a remainder of 3, so it might be impractical. Let me just say this. All right. Since 3 is an element established already, all right, we could say it is congruent, right? That this is congruent to 3, right? We could use that symbol, right, in mod 9. We already have a 3 here, so we're not getting a value that is outside the confines of the set, all right? So we don't really need to do this, right? And if you did do it, there's no sin in that, but watch what would happen. How many 9s can you squeeze into 3? 0, because it's too big, right? But these two things multiplied is what you would subtract. So it would be 0 times 9 is 0. You'd end up with 3. That would be your remainder, all right? The value of 3 is 3. Right? This is superfluous. You don't have to do it when you get an element already established. Okay. Okay. One more. 7 times 5. If you did 7 times 5, you would naturally get 35. And if we divided that by 9, let's see what you get. How many 9s can you squeeze into 35 roughly? 4 would be 36, that's too much, so 3 whole 9s would be 27 is the next best choice, right? And the difference would be 8. Okay, so that's your remainder 8. Therefore this is congruent to 8 in a mod 9 system. This is congruent congruent to 3. And this is congruent to 6. Okay. All right. Now, when you get questions where the value that you're looking for is in a different place, let's try a couple of those. Let's see. I don't know if this is better or worse without the overhead light. I wish it were a better day. It's a little drippy. Okay. Let's see. So to distinguish this, let me just tell you up front. The question in different locations. You'll see what I mean in a moment for these next couple of problems. Let's start with this. Suppose you had this problem, 3 minus 5, and this is a MAT-113 system again, and we're basically trying to figure out what the value here would have to be. This is going to be no different than the types that you had just done. Let's see. The only caveat here is that if you did the arithmetic, you're going to get into some trouble. Let's see. Put this here. I like to always, when I do these, kind of leave some space for work. So I'm trying to like separate out that region, that area. Okay, what we're going to be asked to do in this case is the following. Determine the positive number. Because then if you did this, you'd get a -2 technically. Less than the modulus. That makes the statement true. That's a mouthful. But basically, to summarize that, we're looking for a positive number, so I'll just call that n. And it has to be less than the modulus. And the modulus happens to be, you know, the maximum, really, or the boundary, if you will. Okay. So if, in this case, the modulus happens to be, for a mod 7 system, 7, we're looking for a positive whole number, right, that is going to satiate this condition, all right? That is going to be less than 7 because we can't be under it in the negative realm, all right, because it has to be positive, all right? And we have to be within the mod 7 elements, which is 0 through 6. Remember that. These are the only elements that we're really allowed to have sitting here. So we're going to have to translate, as we often do. Okay. Let's see. Okay. Since we're going to be working on this side of the sort of equation here, on this side we could perform regular arithmetic. Right. Let's try to conceive of a situation that creates a number here. We're going to end up with a bigger number than what was originally written here, right? Because we need something that's not going to produce a negative on the arithmetic side. Now, since we're working with a mod 7 system, let me just give you this little notation here. In mod 7, all right, adding multiples of 7 results in a sum in the same modulo class. In other words, if you count by 7s, right, you're going to get a different number, but the number is representative of the same congruent original number. Let me illustrate what I mean. Say that we add 7 a bunch of times, right? Multiples of 7. What are multiples of 7? 7 times 1 is 7. 7 times 2 is the second multiple of 7, that's 14. Right? 7 times 3 is 21. Even though these numbers look drastically different from one another, they're all multiples of 7, and they all represent, they're congruent to 7. Right? They would all have the same remainder, the remainder of 0. Right? Let's see. So they're in the same modular class. All remainders of 0. Right? They're all congruent. That is what it means to be in the same modular class. Okay. If I took this number, what was there, and I went forward in the same, since I'm working with modulo 7, I just added 7 here to see where I would land in ordinary arithmetic. The number that I would get here is 10. Right? If I were doing mod 8, all right, I would probably add 3 plus 8, all right, in which case I get 11. If I were doing mod 6, I would probably add 3 plus 6 and get 9 instead. If you actually subtracted 10 and 5, you are now thankfully outside the realm of negatives. Right? So this would produce a 5, right, as a result of this. All right. Anyhow, from before, alright, you don't have to translate this. Because it already is an element of mod 7. So what you could say is that the number that is here in a mod 7 system is actually 5, right? If we ended up getting something that was beyond, the boundary, all right, then we would have to do the division and then translate it, right, into a mod 7 element. It already is, as a result of this arithmetic, a mod 7 element. Let's do another one. All right. Here's the condition that happens to be met. All right. If we got a 5 here, let's just verify. Is 5 positive? It is positive. Is it also less than the modulus of 7? It is. All right. So we don't need to go any further with this. It's a little confusing, so we'll do a couple of these. Still aiming at this objective. We want a positive number that is less than the modulus. Okay. Here's another example. Suppose that, again, the question of what you're looking for moves around. Suppose that it was one of the addends, or in this case, subtrahend. So -4. And we're establishing that it is congruent in mod 5. And we're looking specifically for one of the original terms here, rather than the outcome, so to speak. And this is mod 5. Let's establish a couple of things. All right. If now we're working with mod 5, a modular system of 5 elements, then this is the set 0, 1, 2, 3, 4. Right? The last one, well, the first one is always 0, and the last one is always the modulus 5. All right. -1. Okay, so there's still 5 elements, just starting at 0 instead to compensate. Okay. This is congruent to 3, apparently. 3 is an element. All right. But what makes 3? All right. Let's try to figure that out. Right. Essentially, what's going on here is, what makes 3? All right, and bear in mind, we're on the regular arithmetic side here. So it could be something that is outside these elements that is sitting here. There might be several things. Let's see. Well, under ordinary circumstances, what comes to mind is this. Ordinarily, into a thought cloud, 7 minus 4 equals 3. Okay. What we need to do now to satiate this, which is determine a positive number less than the modulus that makes the system true, is we're going to have to do the translation now. Right. 7 would produce, under the ordinary conditions of ordinary arithmetic, this situation would equal 3. Okay. Well, what is the boundary in this case? That's a modular 7 system, so I'm not thinking about that anymore. Before, when it was a mod 7 system, right, to see what would be a congruent value a little bit higher than the boundary, right, we added 7 to the number that was sitting here. All right, so 7 plus 3 was 10. We're working in mod 5 now, so the boundary is basically 5 instead. Let's try to conceive of two numbers, right? One of them including a boundary. And the other thing being the number that was there. This is the boundary. For mod 5, right? What number would you get in this case, right? Under the conditions of ordinary arithmetic, 7 minus 5 would be a legitimate number 2, right? All right. Does 2 satiate this situation? Well, it is positive, so that's great, right? Is it less than the modulus that is in this case, mod 5? Right? Is that correct? It is, right? So the number that would be here, in this case, is strangely 2 minus 4, right, is congruent to 3. Right. The reason why we're doing subtraction, that was starting out that way, so I'm double talking here, not necessary. Okay. Apparently, what you could glean from this is the following. 7 and apparently the number 2 are in the same modulo class. That means that they're congruent, right? 7 is congruent to 2, but we can't use 7, at least we can't keep it, because it is beyond the scope of the set, okay? So we'd have to translate that into this. Okay. All right, one more of these and then we'll sort of shift gears. Are we on time? Okay. Going a bit over here, but it's better that we do. Last one of this type here. Yeah, suppose we had 5 minus question is now here, and this is congruent to 7 in a mod 8 system. Right. Just remember, if you have mod 8, put this up here. That means that this is the set 0, 1, 2, 3, 4. 5, 6, 7. Right? So elements that we would be allowed to use, all right, are bound in this sort of spectrum here. These are the elements that we're allowed to have. Okay, and the question is here. All right, now similar to before, let's see. If I used any of the elements up front, if I use, say, 0 here, under the conditions of ordinary arithmetic, I would have the number 5, right? And 5 itself is an element, so they're not going to be congruent, right? So I really can't get away with doing that. Let's see if I can, for a moment, just kind of reach outside the spectrum for a moment, right? And kind of pull the trick from before, right? When I had the problem 3 minus 5. Right, taking into consideration these facts. Right. This is what the mod 8 system would contain, elements from 0 through 7. All right. 7 is an element. All right. Can't really stretch beyond that. We're concerned now with what makes 7. All right, just know that it can't be negative. And let's say, hypothetically, if we add multiples of 8, which would be like 8, 16, 24. All right. This results in a sum in the same modular class, modulo. What does it mean to be in the same modular class? It means that the numbers are congruent. And they don't look alike, but the sum and the number 8 adding 8 would produce a number that would be congruent. So, let's see. If we took the number 5 and we added 8 to it, we're going to get a sum. It's 5 plus 8 under ordinary arithmetic. This would be 13. All right. So we're just outside of the spectrum for a moment. This is still minus 7. Minus of some question we're looking for, and we're trying to produce 7. What would make 7? Right. Just realize that if I used any of these, it wouldn't be 7. 5 minus 0 would be not 7. All right. 5 minus 1 would be, not 7, would be 4. All right. 5 minus 2 would be 3, 3 isn't 7. And eventually, if you went to 5, you'd get 0. And then if you went into the 5 minus 6, all right, then 5 minus 6 would be in the negative category, and then we'd be violating this condition here. This is unique to the problem. All right. Anyhow, so we stretched beyond that, right? Taking advantage of this fact that if I consider that it's a modulus of 8, then the pattern repeats in multiples of 8. All right. All right. So 0 and 8 are congruent. Right. 0 and 16 are congruent. 0 and 24 are congruent. They all have the same remainders, namely remainder 0. All right. Even if I started with a different number, all right, 5, and then went through a pattern of 8, because that's what modular system 8 requires, all right, you would get a number that is congruent to 5, all right? 13 should have the same remainder of 5. I don't want to drive you crazy, all right? But it should, all right? Here's 5 divided by 8. Here's 13 divided by 8. How many 8s can you squeeze into 5? 1. Pardon me, 0. And then if you subtracted these, you'd get a remainder of 5. How many 8s can you squeeze into 13? 1, that's what I meant. And if you subtracted them, what would you get? A remainder of 5. These numbers, 5 and 13, although they don't look alike, are congruent in a modular system of 8. All right? So adding 8 is not hurting anything, and it may seem a little crazy, but again, whatever the number is here, all right, that's why I used it. All right. So let's go back to this. What makes 7? Using now this number, because it's not going to produce a negative. Now, we could conceive that it would be 6. All right. That this value here would have to be 6. And that's the answer then. Because if we test it with the conditions of the problem, is it a positive? Yeah, 6 can be positive, right? It's definitely one of the elements here. And it's less than the modulus, in this case, of 8. So that's cool, right? That's what the value is. 6. Anybody saw this, right? Outside of this class, right? 5 minus 6 equals, they throw a fit, right? But they don't realize that we're talking about a modular system, right? Okay? It defies logic, you know? At least the original arithmetic logic. Right? That's what we're after. Okay? Is it getting too dark? All right. We could change the operation to multiplication. I'll do maybe one of those. And then I want to give you a nice example. That is real world example. The more of these you do, if you feel incidentally a little intimidated, this is like, wow, just realize what's going on. In your head, it's defying, you know, what we've all been conditioned to this point, to go 5 minus 6 is negative 1, you know, Wolfman. But we're taking into consideration, we're not working with an infinity of numbers, we're working with the 8 elements, mod 8. So there's a cycle, basically a repetition. Let's see. We'll keep these conditions here. But we'll change the operation to multiplication. And we'll see where we go. Looks like it's still visible. Good. That summarizes this. All right, determine a positive number less than the modulus that makes statement true. The statement. Proper English, somewhat. Okay. That's going to represent some. suppose you had this, right? 2 times, I'll be looking for the value here, congruent mod 5. Again, I wouldn't feel bad about establishing some facts right off the bat, right? If you're working with mod 5, all right, that means that this is the set 0, 1, 2, 3, 4. And that's the maximum. All right, the 3 here is an element of this system. It's right there. Okay. And then we will ask ourselves, well, what makes 3? Right. In this case, what makes 3 when multiplied? As we change the operation. Well, under the conditions of ordinary arithmetic, already we're getting in trouble, right? There isn't a number times 2 that is going to make 3 under ordinary arithmetic. Right? 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, and then already we've gone beyond the number. So, we gotta get crafty. Right? What we'll do is, we'll test a few numbers here. Test a few elements. So if we did 2 times 0, we would get 0, right? Under the conditions of ordinary arithmetic, which is why I'm using that symbol, right? Right? That is an element, right? So that's perfectly fine. Right? If you did 2 times 1, you would get 2 under ordinary arithmetic. And if you went to 2 times 2, you would get 4. Right? And so far so good, it's not 3, right? That's not 3, that's not 3, that's not 3, that's exceeding it, right? But we're okay. The thing is that at this point, we've hit basically a maximum. Right? And if we did the next one, 2 times 3, we would get 6. All right? All of this is ordinary arithmetic. Okay. When we have exceeded the maximum here, right, what we're going to do, make sure you turn the light on. Is that better or worse? I think I may have to at this point because it's such a cloudy day that it's only going to get worse, darker and darker. What we'll do is we'll try to translate this value. Right. Translate this into one of the elements that is in here, since it's exceeding 4. Right? And in that event, I'm going to go back to what we had done, which is division. We divide 6 by the modulus, which is 5, all right, and see what the remainder is. How many 5s can you squeeze into 6? 1, and the difference is 1. So that's the remainder. That means that 6 is congruent to 1. And for reference, I'll just put this here. Okay, 2 times 3 under the conditions of mod 5 is actually 1 rather than a regular arithmetic system, which would be 6. Okay. That, although it's helpful, right, it's not 3. So we would have to go a little bit further. I need the space, so I'm going to write upward here. Let's do 2 times 4. under ordinary conditions would be 8, right? But 8 again is exceeding the limit of the modular system. So what we would do is this: we would take 8 and we divide by 5, and then we'll get the remainder. How many 5s can you squeeze into 8? 1, which is 5, and the difference is 3, and voila, there we are. All right, 8 is congruent to 3. 8 is congruent to 3. All right. So if this is basically what we just did, 2 times 4 equals 8, and we know that this is congruent to 3, and that's what's sitting in this position really, all right, then that means that this number is 4. Okay. I think it's better to be very thorough with this stuff, so I don't mind going over time, really. Suppose you had this situation. 3 times something is congruent to 0, and this is mod 6. Again, establish some points here. Right? If we're talking about mod 6, that means that the set is 0, 1, 2, 3, 4, 5. And stops at 5. Okay. And we're really asking, well, what makes 6, what makes 0, right, when multiplied? Okay. 3 times 0 itself would certainly be true, right? If we tested a few. It's dying. That. Three times 0 is in fact 0, so that's definitely one of the possibilities. All right. The condition, I ignored it last time. I really shouldn't have, to verify. I mean, the answer was correct last time, but I really should be looking at this. Determine positive number. Let's try more than them. All right. All positive numbers less than the modulus that make the statement true. All right. 0 is one possibility, right? If the modulus is 6 in this case, well, 0 is not technically positive, right? But that is one of them, so we'll try to figure out the other things that are beyond 0 that are positive. Okay, so we did, let's see, 3 times 1 equals 3. Under the ordinary conditions of arithmetic, that's not equal to 0, but that's not violating any condition because 3 is an element of the set. Right. 3 times 2 is equal to 6. That is exceeding the limit. Okay. All right, so we got to be careful. We would, in an instance like this, have to translate them. Yes, it is a modular 6 system, but notice that the maximum is really 5. All right, it was 0. We would have to basically translate this. So we'll see what number this really should be. Okay. Here's 6 divided by 6, which is just 1 naturally. The difference is 0. This is remained a 0. So that means that 6 is congruent to 0. All right, so that's one of the possibilities then. All right. All right. 0 is legit, but so is 2. All right, since we're trying to consider all things and we really want the positive things. 2 is less than the modulus, so that's a legitimate answer. Right? There'll be at least another one. Right? But let's keep going. Right? Let's see what happens after this point. Right? If we did 3 times 3, all right, under ordinary arithmetic we would get 9, which again gets us in trouble, right? Because this is outside the boundary here. So if we did this, 9 divided by 6, 6 goes into 9 roughly once. The difference is 3. The remainder is 3. That means that 9 is congruent to 3. So that would be here. Starts to be a pattern here. Look at this. All right, we're getting in the mod 6 incarnation of arithmetic 0, 3, 0, 3. All right, I bet you the next one is another 0. Let's see, if you did 3 times 4, under ordinary conditions it would be 12, right? One more of these. Let's see. Let's do 12 divided by 6. 6 is going to 12 twice, which is 12. The difference is 0. That's the remainder. That means that it means that 12 is congruent to 0 as well. They're part of the same modulo class, all right, to use a phrase. All right, so this is really 0 again. So 4 is another possibility. And 4 would also be fitting this condition. 4 is a positive number that's less than 6. All right. All right. If we did 5, all right, that would technically be the limit, but I'll bet you any amount of money it's going to be 3 again. All right, here's proof. If you did 3 times 5, you would get 15. Well outside the confines of the modulus. So we translate 15 divided by 6 goes into this twice. The difference is 3. Remainder 3. That means that 15 is congruent to 3. Yep. All right, and at that point, we can't use 6. We would get 18 in theory, but it wouldn't be a number that is less than itself, right? So, as for the positive numbers, 2 is one possibility. That would make this statement true. 4 would also be a possibility. The next example is kind of interesting, but just in case it comes up when you're doing your MyLab stuff, I'd like to take the time to do it. The more you do this, the more comfortable with it you'll be. Positive number less than the modulus. Okay. It's on its way out. Alright. Last one of this type, and then we'll do word problem. Okay. If you have 3 times a factor, and we're saying that it is congruent to 2, and it is also in mod 6. Okay. We kind of did this work already, so this will go really quickly. Right. But we're switching the value here. Right. In the last problem, it was 0. This is if we're trying to get 2. Right. We had established just a moment ago these possibilities, right? That 3 times 1 is congruent to 0. That 3 times 2 is congruent to 3. That 3 times, am I missing one? Yeah, more slightly, sorry. 3 times 0 is 0. 3 times 1, stupid, is 3, sorry. 3 times 2 is 0. 3 times 3 is congruent to 3. 3 times 4 is congruent to 0. 3 times 5 is congruent to 3. All right, and that's basically exhausting all possibilities, right, in a mod 6 system. All right, we've used all the elements here, and this is what they are congruent to. All right, and we're concerned with congruency because this is what it is. Now notice something. There's only 2 choices here. Ultimately, 0 or 3, 0 or 3, 0 or 3. So is there anything that is ever going to be 2? It's not going to happen. Right? It means basically that there's no solution. Right? There isn't anything, nothing congruent to 2. Okay. All right. Just in case it comes up. All right. Now here's the last thing. This will be a little bit more amusing, I suppose. A practical application of this. A word problem. All right. Consider this. Work schedule. Wish that broke a little bit. That's really nice. A work schedule like so, right, where a person is six days in a row on schedule and 2 days in a row off. All right, so what you might say, on meaning working and off meaning not working. This would be not to go off on a tangent, but in Star Trek, the original series, the computer used to occasionally say that working, you know, when it was trying to calculate something. It would be a delay. Right. Okay. Let's answer these questions. Right. If today is the 3rd day. Let us determine question A, whether the person is on or off schedule. All right, 60 days from now. Which means, again, on means working. And that's faint. And this means not. It's done. That is the end of that. All right, green. Okay. On. Oh, that is so much better. On or off. off, working or not working, right? It's not really asking for the day, right? In this case, you're not asking, is it Sunday, all right? Is it Wednesday or what have you, all right? And I know that normally when you have a week, you go, well, a week is 7 days, you know. That's why I'm specifying this. This is a person working in 6 days in a row and then finally getting a break, which means that their days off are gonna constantly shift forward, all right? You're not gonna be like exclusively gonna have Saturdays and Sundays off. A person is 1 week, maybe it's gonna work that way, and then the next week after that it will be, you know, Sunday and Monday, and then the week after that it'll be Monday and Tuesday off, and so forth. Okay. A couple of things to establish here. Right. We want to translate this into a system. This is a word problem, and we want to basically conform to the modular system. We're going to basically translate into a modular system. How many days are we talking about total? Right? Again, a normal week is 7, but this is weird, this case, right? How many days total are we working with? 8, technically, right? 8 days. Okay. So in terms of a modular system, right, this would technically be mod 8. Okay. If it is mod 8, let us establish, all right, what is the elements? What is the set going to look like? All right. The set would be 0, always starting with 0, 1, 2, 3, 4, 5, 6, 7. And it would be, basically the schedules would repeat in cycles of 8. Let me put this in a different color for reference. All right. Okay, multiples of 8, cycles of 8. Okay. What that basically means is that day 0 should be congruent to day 8, right? Okay. Under normal conditions, right? And 16 and 24 and so forth. All right. Now, the actual problem is asking, okay, whether the person is on and off 60 days from today, and today is the 3rd day specifically. The 3rd day technically would be the number 2 here, right? Okay. And so let's say that you started with the first day of work, and I'm just going to put a W above those days, right, to represent on for working. Working, working, working. Right. W3 would also be 1, 2, 3, 4, 5, 6, and then N for not working, N for not, according to the very first week, right? And we're starting here. 3rd day in, with 0 being the first, right? 1, 2, 3, this person would be working. Based upon that condition, 3rd day working. All right, let's figure out what it would be 60 days forward. All right, we would have to basically now translate 60 from regular arithmetic into mod 8 element. right? Which means what? It means that we're going to take 60 and divide by 8. All right? How many 8s can you squeeze into 60? 7, right? Which is 56, and the difference is 4. Okay? If that's the remainder, then that means that 60 is congruent to 4. Okay, let's look now at day 4. All right, day 4 would be here, where the 3 is, ironically, because it's 1, 2, 3, 4, and the person is working. So the conditions have to be congruent, right, with the original schedule, right? And this is an example of a person. Oh, you know what? I have to correct myself. Pardon me. No. I'm sorry. Add 4, all right? Not look at 4. All right. All right. 4 added 2, all right? From the start of 2, all right, in this list. It's the 3rd day, that's technically 2 here. Go 4 days forward. 1, 2, 3, 4. Here, all right? The person is off, they're not working. Okay, again, because it shifts, all right? All right. Week number 1, if you will, all right? Let's just say that that was Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Saturday, the person normally has off, right? At least if they have a nice job, a non-torturing job, all right? They would be off, not working, all right? But, all right, it's gonna constantly shift, all right? Anyhow, from the start, move 4. And you land here, right? Which means that the person is off. Okay. Let's do another one, especially since I fudged that in the middle of it. All right. Okay. I'll just tweak this slightly. Let's do 82 days from now. We have established a system here. And I'll erase some of this for the sake of space. And clean this up a bit. Do my work here. Right. Still starting on the 3rd day. But moving 82 days forward, all right? 3rd day person is working, all right? We'll see whether they're not working or they are, all right? 82 days from the 3rd day, from the start of here, okay? This is the start. Destroyed. Okay. All right. We in the first problem translated 60 into a mod-8 element. All right, and that would be 4. What we're going to do now is we're going to translate 82 into a mod-8 element. In the same process, we're going to take 82 and we're going to divide by 8. All right. How many 8s can you squeeze into itself? 1, and the difference is 0, drag down to 2. How many 8s can you squeeze into 2? You can't, it's too, this is too big, that's too small, so 0. 0 times 8 is what you would actually write here. 2 minus 0 is a remainder of 2. Alright, and that means that 82 is congruent to the number 2. We've translated the regular number into a mod 8 element. Alright, so if this is where we started, we're going to move 2 spaces forward. Alright, 1, 2. Alright, that means that you would now be here. Alright, is the person working on the 4th day to start with? Yeah. Alright. Alright, so a person in this case would be working on the 82nd day. Okay. And it would technically be their 5th day at that point, right? 1, 2, 3, 4, 5. Alright, one more of these. Let's figure this out for behind, instead of forward. And we'll do it, let's see, 124 days earlier, right, days ago. Were they on schedule or were they off schedule 124 days previously? We're still going to do the same thing, really. We're going to translate (124) into a mod 8 element via division. So if we have 124 and we divide by 8, how many 8s can you squeeze into 12? 1, which is 8. And the difference is just 4. Drag down this 4 here, readdress the question. How many 8s can you squeeze into 44? 5. All right. And that would be exactly 40. All right. And the difference here would be 4. So that means that the remainder is 4. And therefore 124 would be congruent to 4. Okay. So if we go back to this very sloppily drawn thing here, and I'll just fix what's broken. That's the W for working. This is the number 4 here, element, and this is the 3rd day, which is number 2, because we start with 0. If you start here, right, and you go 4 days forward, right, 1, 2, 3, 4, right, person would be off. All right. Okay. All right. I know that we're talking about going back in time, but we're using a cyclic system here, so we're just going to go numerical when we're talking about this. All right. Anyhow, 124 days in the past. Oh, you know what? Let me correct myself. I do have to be careful of that. I am going backwards. I'm sorry. Let me, since I'm stretching here, I'm going to take this, all right, and just kind of rewrite it here, because I really do have to compensate because of the direction of time. All right. Here is 0, 1, 2, 3, 4, 5, 6, 7, right? And again, just above it was the original situation. Of working, not. And I'll erase this because it's getting a little messy. Here again is where you would start, because this is the 3rd day. And now, what's going to happen is one of two things. You could basically, you're going to be moving in this direction because it's a go. Previous. And you could basically count this way and then just automatically, go to the back of the line here and go the extra 2. Or duplicate what would have been there on this side. So I'll do it both ways. All right, I'm going to count 4. All right, 4 days. 1, 2, and then if I'm not drawing anything else, 3, 4. All right. Do be careful. I mean, it coincidentally landed in the same answer that I just gave you. All right, but it would be more accurate to go in the appropriate direction here. So just be careful of that. Okay. You could make a mistake. Now, if I just did the same thing, I took the pattern that would have been here and put n, all right, 7 and 6, and then just counted like this. All right, yes, it would land the same result, but 1, 2, 3, 4. This is where you stop. You really should be headed this way. Okay, so on the sixth day, according to the original sort of paradigm here, all right, the person was not working, they were off. Okay. That's about it. Okay. In case it comes up, all right, when I was looking through the textbook, there was another problem here, and they just mentioned this fun factoid, which I'll write. A modular system, for reference, this is a fact, all right, to know if it comes up in your work. All right, a modular system is a commutative group. All right, what does that mean? It means that it would satiate the first 4 requirements to qualify as a group, all right? And then the extra 5th requirement is that it is also commutative, all right? Just to summarize, let me give you this real quick. Okay, what does it take to be a group? Let's see, it has to be closed under the operation. So if you're talking about adding, if you added any of the elements together, would it produce just another element of the same set? Then it's closed, right? If while adding under the operation you were to get something that is not one of the other elements, then it would not be closed. 2, it would have the appropriate identity element. I mean, traditionally it would be 0 or 1, but just to be careful. And it would be good if you had a table to look at. You would pull that trick, basically trying to look for a cross, and using a table, right, look for a cross. So for example, here, let me show you this. I find this a little bit more satisfying. It was an older thing from the last section. All right. When you match, all right, the column headings in the grid here in the table, all right, with the row headings in the table. Notice this is alpha, beta, gamma, delta. This coincidentally is alpha, beta, gamma, delta. If you match the row headings here in the table with the column headings here, they will cross exactly where the identity element is. Sometimes it's not so obvious, it's not in the middle. If you have something like this, for example. The row headings here, if I can get my finger in the way, 0, 1, 2, 3, 4. You would look for the column heading in the grid, right? That is the table that is not whatever color this is, it's kind of a flesh color, a shaded flesh color. So 0, 1, 2, 3, 4, and match it, look for a cross that forms from the row headings here. Column headings, row headings, 0, 1, 2, 3. In this instance, all right, the identity element would be 0 for this particular group. It would be that point of intersection, basically, 0 itself. Okay. All right. Let's see. All right. Just to complete this thought. Into a tight corner here. Look for a cross in the table. Right, the point of intersection, 3. There has to be inverses, right, for each element, also present. Right. You can remember a formula for that. If you take what are thought to be inverses and perform the operation, like let's just say it was hypothetically adding, right? If you combine them, or if it was multiplying, right? What inverses produce is the identity element. So in the example that the book had for a commutative group, let's say the identity element would say 0, and that usually is either the case, it would be 0 or 1, right? It doesn't have to be exclusively that, but they tend to be, right? Then if your operation of 2 factors or 2 addems or whatever produces the identity element, then if you test them for all of the elements in tandem with one another, if all of those inverses then therefore are proven to exist, then it qualifies this condition. You have to have an identity element, you have to have inverses for each element. Okay. All right. The next thing in summary is 4. That it's associative. This is even more tedious though. You would have to test out the associative property for all of the elements. All right, which is a pain in the neck, and they usually just tell you that to begin with, and then you test out the commutative property. Commutative. Okay. All right. In the case of the commutative property, there is a shortcut similar to these things. If you see that there's symmetry along what is called the main diagonal, you could assume that the group is commutative. Okay. All right. So just to close, all right. In summary, the group has to be closed, meaning if you perform the operation, it only produces more of the same. The operation only produces more of the same elements. Right? It doesn't produce something other than that. Right? If you had a table again, you could kind of stare at all the elements and go, is there something weird in this table that shouldn't be in the set? All right, it doesn't come from the set, then you can rule it out visually that way. All right, an identity element has to exist, right? And if you have a table again, you're looking for a point that they cross, right? There has to be inverses for each element, and if they are in fact inverses, you can test by adding or multiplying, what have you. If it keeps producing the identity element only, then they are truly inverses. All right. And then it has to be associative and commutative. Okay. Let me leave it at that. Okay. As we're going along, it's like 2:15 now. All right. Thank you for listening. Try section 9.3. As you can see, it's kind of involved because it's new, right? And it does defy what we've all been sort of conditioned from birth to go, okay, 2 + 2 is 4, not and necessarily in a modular system. Okay? Give it a whirl. All right? I'll see you, folks. Be safe.